Okay, you ready for a little bit more math? So now we're going to just kind of review everything we talked about, this whole chapter. So we talked about Kc, that's our molarity, right? And remember, Kc, C means concentration, concentration means molarity. That's what this means. That means, well, I'm just going to say that. It means molarity. Kp, pressure. It's always atmospheres. P's always atmospheres, right? Always atmospheres. So if you're going to write these, it's just remember products raised to the coefficients over reactants raised to the coefficients, right? So you can write this either way. So you can write it with Kc's, which would be concentrations, or Kp's, which would be pressure. Okay, here we are. So I'm going to just throw a bunch of problems at you now, just like you're going to get on a quiz or exam. They're not all the same, but all different. Some are easy, some are hard. So we're just going to do a couple of these. So we have a mixture at equilibrium has 0.4 atmospheres H2, 0.3 atmospheres I2, and 0.2 at HI. Calculate Kp. So try this. I'll give you 2 minutes for this one, and then type your answer in the chat, and then we'll go over it. Don't make this one harder than it should be. And again, if you're watching this later, make sure you try this one now. So I'm seeing, so you see this one, right? This one's not a hard one, right? Even though we've been doing these crazy ice tables, this one I'm giving you all the equilibrium. All you have to do is plug it in, right? And they're already in peaks, so you get 0.33. So yeah, very good. This one's just a really super easy one. Okay, now let's just take a little foray into Q's and K's for a second. Okay, so remember Q. Q, you have to calculate to see which way the reaction's going. If Q is greater than K, right, then it's going to go backwards. So remember, I always think of it as like a pendulum. I don't know if that helps. And that's where we want to be. This is when Q equals K. If Q is greater than K, which is over here, it's got to shift backwards, right? So it's got to go backwards. We've gone too far. If Q is K, here we are, we're right at equilibrium. If Q is less than K, so if we're over here, then it's got to shift back that way, right? And so again, we need to figure out which way it's going to go, and we always need to check this unless we're only given reactants or only given products, then we know which way it's going to go, right? It's just another way of seeing which way it's going to go. Here's Q less than K. It goes, right? Q equals K. And Q greater than K. It's just a different way to see it. Okay, so now let's practice that. Here's a new flask. So now, same temperature, so we're not going to change our K. So if it says same temperature, that's kind of just saying K is not changing, right? And so I gave you your K that we just calculated. Now I want to know if it's going to go in the forward direction or reverse direction. Okay, so try this. Tell me the answer is either forward or reverse, or towards reactants or towards products. Which way is this reaction going to go? All right, so try this one. I'll give you like a minute or two, and then we'll go over it. Right, so this one, the keys here is it's the same flask, same reaction, same temperature, we just change the concentrations. So we just put those concentrations into our K, right? Just like we did before, we just put the new ones in. And now I'm just calling it Q because it doesn't say equilibrium, right? So I put it in, we get an answer. The answer is 2.7. So our Q is greater than our K, right? So if our Q is greater than our K, right, here's when they're equal, Q is bigger. It has to go whoop, back towards, it has to go towards our reactants, which means that it's going to go, so it's going to spontaneously go backwards. It's going to go towards the reactants to try to reestablish that equilibrium or to establish equilibrium. And so that's how we use Q's and K's. Okay, now here's another one. And again, all sorts of different problems are coming at you now. And by the way, you can totally complete all of your equilibrium homework. We've done everything. All right, a tank is charged with HPR, so its concentration is 2 molar. If Kc is 25, find the concentrations of all 3 gases. Okay. So again, I'm going to give you a minute on this one, and then we'll do it together. I might give you a few extra minutes on this one. Okay, how are we doing? Okay. Need more time?
If more time, yeah.
Okay, give me a couple more minutes. By the way, you'll see I did these as C's, so just leave these as C's. You don't have to convert anything with the P's. Okay, so let's look what we got. So how do you start this problem? First thing you have to look at. So if you're like, so you got a KC, all right, check on that. Good. And then all they're telling us is that we have 2 molars of HBr. So all we know is we have 2 molar of this. That's it. And if we want to figure out our equilibrium concentrations, we have to do an ice table because they've given us an I, an initial, but they want the E's, right? And so we got to figure out an ice table, right? So here's our reaction. H2 plus Br2 goes to 2 HBr. So we have an ice table. And again, I will always have this meter in a second. That's our ice table. And all we're given is this. That's 2. Well, they're all molar, right? That's 2. So if that's all they're telling us, that means that everything else is 0. Okay, so here's one where we're only given products. So this means this reaction is going to have to go backwards, right? So that means we're going to go down by 2x, up by x, up by x. But remember, we always write our equilibrium expression the way it's written. So when we write our K, it's still going to be HBr squared over H and Br, right? So even though it's going backwards, we still write it the way it's written, right? So it's always going to be written the products over the reactants, right? And so that's kind of the key to this problem, which, okay, hold on. 0, 0, 2 is going to go down by 2x, right? And the reason it's a 2 is because of this 2. The others are going to be 1s because there's nothing here. And then we have x, x, and 2 minus x. So then when we write in our equilibrium expression, which I'll just write it really quick. So when we do this, it's K, which is given to us, which is 25, equals, well, this doesn't look like pretty math, does it? 2 minus 2x squared over x squared, right? They're both x's. So that math, that doesn't look like fun, does it? Right? Oof, that doesn't look like lovely math at all. So let me show you the shortcut I did on this one. Since they're both squared, I just ignored it, right? Since that's squared and that's squared, I'm like, meh, that was my way of simplifying that math, right? Because they're both squared. And then you get x is 0.286. But this is not our answer, right? This is our 75% of the way answer. So we have to put this back into our ice table. And so I kind of just didn't use that last significant figure this time because this only has 2 sig figs and this only has 2 sig figs. So I only used 2 sig figs here. You could have used 3, it doesn't matter. So our Br concentration is X, our Br2 concentration is X. Now, how do I know this again? All I'm doing here, I'm looking at this. I'm gonna plug in my X. See, I'm gonna plug in my X for these right now. So I'm just gonna plug this in. So 0.29, 0.2, and then this is gonna be 2 minus that, which is just 1.4. And so here are our answers. Now again, this is we're like at 95% here, right? So we're at 95%-ish on this one. Yeah? We need to check it. And again, I always suggest that you check. And the reason that we check this is so we know that we did it right. So how do we check it? We would just put in K, which is 25, right? 1.4 squared over 0.29 times 0.29. And when you do that, you get 25.
Professor, I have a question before move on. Back at the ice table, you always put the reactants as a plus X and plus, or at least a plus sign there. It's always going to be plus, and then the products are always going to be negative?
That's a great statement. So to figure out, or a great question. So to figure out these pluses and these minuses, you have to figure out your Q, right? That's why we have the Q. The Q tells us which way it's going to go. Now, the only thing we're given here is that this is a 2 and this is a 0 and this is a 0, right? So therefore, since all we have are products, that means this reaction has to go backwards. If it goes backwards, the reactant has to increase, this reactant has to increase, and this product has to decrease. That's where these signs come from. Does that make sense?
Yeah, so what would it look like if it was the reactants were negative?
Okay, so let's say instead of, I'm just gonna go back here and change something really quick. I'm going to say, what if it says that Br2 and H2 were 2? So this is 2 and this is 2. So then this would be 2, 2, this would be 0. That means it has to go towards the products. And so therefore this would be plus x, and this would be minus 2x. Does that make sense? So you have to look at which way the reaction's going to go. So like, for example, we'll just do this really quickly. I have absolutely no idea what this is going to be the answer. Actually, no, I kind of do.
What'd that be?
What if these were my initial concentrations, 2, 2, and 3? Which way would the reaction go? I don't have a calculator. So how would we figure out which way the reaction goes? Any idea? What would we do?
We would find Q.
Exactly. So we find our Q, which would be, wow, it's not a K, right, Q. 3 squared over 2 times 2, right? So that's like 9 over 4. I don't know what that is. It's definitely smaller than 25, right? So Q is less than 25. And since it's less than 25, that means our reaction has to go forward. So therefore, that means this is a negative x, this is a negative x, and this is a plus x, plus 2x. Right? So do you see it's your Q that you're using, that's what's telling you the signs. Does that make sense?
Yeah, it does.
Yeah. So in this case, so if I just erase everything on the slide, because all they gave us was the product, we knew that this is all they gave us, so it has to go backwards. So this has to be positive, this has to be positive, and this has to be negative. So you're using your Q, but since there's no numbers, you can just see that it has to go backwards. Does that help?
Sorry, I'm allowed to just put 0 because that's where I get stuck. I'm like, I feel like I need to put something there, and putting 0 there just feels wrong.
Right. Yeah. So that is, it's you're like, I feel like I should put anything. I should put something. If they don't give you anything, they don't say anything about a reactant or product, you just assume it's 0. So that's an assumption. If they don't tell you anything, you're like, oh, we must not have any. So that's when you put your zeros in.
Okay.
All right. So we write our K, which I'm seeing a few people that are typing it. Okay, so a few things. K, and you see how this is Kc? It says concentration. Even though these are pressures, and again, this kind of gets some people sometimes, it's asking for concentration. Concentration, we have to do molarities. So we have moles and we have liters, so we're going to have to do molarity. This isn't going to be in pressures, even though it looks like it should be. So our products are H2 and F2 over HF squared. Remember, however it is written is however you put it in. So it's always products over reactants. Then we need to find our molarity. So our equation, and I'll do this much nicer in 1 second. It's 2HF goes to H2. Let me just move that a little bit further apart. Plus F2. ICE. And we've got our ice table. Right? And so we need to figure out what our molarity is, right? And so we have moles. Let me just erase some of this. We have moles and we have liters, so we need to find it. And I got home, so I could actually use my calculator. Divided by 3. So our molarity is 0.05 molar. right? And it's HF, H2, and F2. So we have 0.05 molar of all of them, right? But now they're giving us 0.5 molar of all of these. So we need to figure out, they're giving us them all, right? So this should be like, what? I don't understand. How are they giving us all of these? Okay, well, all right, we're just gonna say they're giving us all of these. So you're like, what do we do? This should be your hint. We don't know which way it's gonna go, right? So we need to find our Q first. So to find our Q, we put these numbers into our Q, which is again, exactly the same as K. We just put the numbers they give us. So 0.5, times I guess 0.05. Again, I'll do this neater in just a second. Over 0.05 squared, and then we see what we get, which we can already see. That's going to be 1. Okay, so now let me just show you this neater. So each of our concentrations are 0.05, right? Just like we said. Then we look at our ice table, 0.05, 0.05, 0.05, but they're giving us all 3. So we have to find Q because we don't know. The reason we have to find Q is because they're giving us all 3 of those. So usually what's been happening on a lot of questions is they just give us 1. Well, if they only give us reactants, we know it's going forwards, right? Or if they only give us products, well, then we know it's going backwards. But they're giving us reactants and products. So now we need to use Q to see if it's going to go forwards or backwards. And again, Q is pretty easy to see. It's going to be 1, right? So now we compare. Kc is 0.1, Q is 1. Our Q is bigger than our K, right? So if we do our little, I like to use a little pendulum, right? Here's when Q and K are equal. If Q is bigger than K, it's got to go backwards, right? So that means that we're going to go backwards. So our our products are going to decrease, and I'll show you in a second, and this is going to increase. So in your ice table, how do you show that? So this one's going to go up by 2x, because again, it's going backwards. So that means our reactants are going to increase because it's going to go backwards. And our products are going to decrease. And again, it's 2x because of this 2, and this is just xx because those are both 1s. So now we start with our math part. So here we are. That's your ice table. Well, anyway, you get it. That's your ice table. It's just a little bit crowded. So this part, again, this is just the beginning of it. Now we need to solve for our x, right? And they're only asking for HF at this point in time. So when we solve for our x, here we go. Let's just say I just solved for it. We're going to say x is small. Now, a lot of times people get confused. They're like, well, which one do I cross off? Okay. Sorry, I have to go back here. It's the reactant that you're going to cross off, right? So it's this one right here. You're assuming there's no change in the reactant. So when you do that, and again, the math, if you have questions on the math, we can go through that another time. You get 0.02 after you solve it. So when you get 0.02, that's not your answer. That's the change, right? So that is the x. So we need to plug it in. So when we do that, we get 0.0920, right? And if you get close to that, it's good enough. It should have 3 sig figs. So if you got like 0.919 or 0.0921, all of those would be okay. So this is kind of this is probably like the hardest the ice tables get, right? Okay, so now let's try another one. Okay.
Can you go back for just 2 seconds?
Oh, yeah, sure, no problem.
Real quick.
Right there?
Yeah. Okay. Okay, thank you.
No problem. And if you have a fancy graphing calculator, by the way, you can just put this whole thing in there. If you want me to help you with that, I can't because I don't know how to do that in a graphing calculator. But if you have a fancy one, they can solve the whole thing for you. It's lovely. Okay, So now this one, I'm going to help you a tiny bit because this one has a little twist to it. Not a big twist, just a tiny one. So this one has an equilibrium flask that has, so at equilibrium, it's telling you what they are. So it's telling you, here's the equilibrium concentration. So it's literally saying it. But then it's saying 1 atmosphere of NO is added to the flask. Find the new pressure of NO. So it's giving you the equilibrium concentrations, right? It's saying they're all 0.25, 0.25, and 0.4. But now we're going to add a little bit of NO. We're going to add 0.1 of this, right? So we're kind of changing it up. So I kind of like added a little piece to the ice table here. So these stay the same, but now NO was added. So instead of it's going to be 0.4 plus 1, so it's going to be 0.5 NO because we added a little bit. So now these are our new concentrations. So now we look at the change. And so this is the new piece. This is the little, like I said, there's this tiny little piece. That's the new piece because I added it. Now it's the same problem. So this is, I think, our last one we're going to try. So try this one, and then we will go over this. I'll give you like, actually, this one's not so bad. I have to give you your K. Hold on 1 second.
Is this on the printouts or are these just added?
This one is extra.
It is extra, right? Okay.
Yeah, this one's just an extra one. So for this one, plus X, and then this is going to be minus 2X, because let me just go back. Just really quick here. Yeah, I didn't give you your K, so you can't solve this one without me right now. Yep, because your K was in a different problem, so my bad. So I haven't given you a K, so I'm going to show you how to do this one. All right, and so this one was going towards our reactants in this case. So how did you know this one was going towards your reactants? Because I didn't give you your K, which I'll give you in a second. You can actually tell by Le Chatelier's principle, right? Because if we add some of this, that means it's going to shift backwards. So we know that our reaction is now going to go backwards towards reactants because of Le Chatelier's principle, because it says we added 0.1 NO. So we added NO, so it's going to go that way to reestablish equilibrium. So that's how we know that this is a negative and these are positives. It's got to go backwards. Okay, so again, this one, I said this one had that little twist in it. And here's your K. I still, see, I forgot to give you the K. That's K. I need to add that into the slide for next time. So I forgot to give you K, so you couldn't have solved it without it. So this was given to you, 0.256 or 2.56. Hold on 1 second. You can actually calculate it. Who can see? Wait 1 second. Now you guys can just see me. Okay, now you can see this. Right, yes. Who can see how, even though I didn't give you your K, can anyone see here how you can calculate your K? So I didn't give you your K, which is a mistake, but technically I don't need to give you your K. Can anybody see why I don't need to give you the K?
Nope.
Feel free to type it in the chat. Yeah, we gave you the equilibrium concentrations, right? This one says at equilibrium. Here's a value, here's a value, here's a value. Here's our reaction right now. So you can literally just calculate your K, right? So it's going to be NO squared over N2 times O2. So you literally just plug it in. So 0.4 squared over 0.25 times 0.25. Right, and that gives you, I can't remember what the value was. So you can, even though I didn't give you your K, you could have calculated your K. You didn't need me to give it to you. So if this happens again and you don't have a K, check and see, were you already given the equilibrium concentrations? Because then you can find your K from there. I think it was 2.5, but I can't remember. Okay, so we did this. Here's the K, yeah, it was 2.56. So we got our K was 2.56 from using, again, these equilibrium concentrations. That's how we got K. And again, here's your X. I just solved it all at once and got my X. And again, but that is the change in X. So now to get our pressure of NO, we just plug it in. Oops, sorry. So we just wanted the new pressure of NO. So it is 0.444. And I know these problems take a bit of a time. I wish we had more time in lecture where we could do these forever, but we don't. But homework 2, equilibrium part 2 on Chem 101, it's all ice tables like this. And you actually can drag and drop the variables to the ice tables to help you walk through the actual problems. So hopefully once you finish homework part 2 for equilibrium, you will be much more comfortable with these ice tables. Okay, so let me just, this one, don't worry about this one, hold on. This one, we are going to, this is a different problem. We skipped this problem. Here's one more I just want to talk about really quickly. So this is going to be our last problem. Let me just share this with you. Sorry, my computer and Zoom are like fighting with each other right now. Okay, so now just a real quick exothermic, endothermic review, right? So endothermic absorbs energy, right? So it's positive and it goes on the entering side. So if it's endothermic, we treat it as a reactant. Exothermic as a product. Endothermic is positive, exothermic is negative. So those things should always be in your brain. So for example, this would be endothermic or exothermic. This reaction here, endothermic or exothermic?
Endothermic.
Yeah, and how can we tell? Because it absorbs energy, is on the entering side. So energy is going into the reaction, right? So now it's not quite right. The 80 is supposed to be under the AB, but I just want to show you this. So equilibrium would be 80, 20, 20, and pretend every time I open my PowerPoint, this shifts. So I kind of given up. So at a higher temperature, when you increase the temperature according to Le Chatelier's, right? If we increase the temperature, it's going to shift that way, right? Which means this will decrease. Let me erase that, right? So this will decrease. Both of our products will increase, right? According to Le Chatelier's, that should happen. So therefore, at a higher temperature, our reactant actually decreased and our products both increased. Now, these numbers here, these are just like fictitious numbers I'm just throwing in there. You would have no idea that it went down by 10. I'm just using numbers to show you this. So if we plug it into our K, you can see our K will actually change. So remember that temperature is the only thing that's going to change. And if we have an endothermic reaction and we add energy, our K will actually increase, right? So just remember that temperature is the only thing that can change our equilibrium constant, right? Only temperature. Okay, so that's all with equilibrium. We're going to take a break from ice tables.
I have a question, Professor.
Go ahead.
I had read somewhere where it said that if you, like, let's say you have an endothermic reaction and it asks what happens when you add it on the end of the reaction to like the product side. Where does the reaction go?
So you're saying an endothermic reaction, So just like this one. And what's the question?
Yeah. Like it asks what would happen if you added energy to like the end of it.
Then it wouldn't be endothermic. So if energy was over here, then that wouldn't be an endothermic. To be either endothermic or exothermic, it has to be written as a reactant or a product. But if you added energy to an endothermic reaction, maybe that was the question, like what happens when you add energy?
I think so.
Yeah, so if you, so think, instead of energy, let's use heat, because heat is energy, and we'll talk more about that next month. So if you add heat to an endothermic reaction or add energy to an endothermic reaction, you treat it like a reactant. So see how we've written this as a reactant? So if you add energy to this, so just like we did before, we add this, that means it's going to shift the whole reaction over to products. And so therefore our products will increase. So the concentration of our products will increase and the concentration of our reactant will decrease because the whole reaction is going to shift the other way. So let's do it with an exothermic reaction.
So if we decrease energy, then it move towards the reactant side.
Yes, exactly. Because you treat energy like a reactant or product. So if you decreased energy, that's an arrow going down, then it would shift this way. So the reactant would increase and our products would decrease.
Okay.
So I'm going to do the same exact reaction, but this time I'm going to make it endothermic. Exothermic. So if you add energy to an exothermic reaction, it's going to shift towards the reactants, right? Because again, we treat it just like a product. I'm just going to do that in a different color. So if we add energy, it's going to shift towards our reactants, right? So then therefore our reactants will increase and our products will decrease. And that's why it changes K. Now let's do it the other way. If I decrease energy, or this would be the same as saying if I decrease the temperature or if I lower the temperature, then which way will the equilibrium shift? That's my question for you. Towards the products, right? So it's going to shift towards the products, right? And then we would have our reactants would decrease and both of our products would increase, right? And again, that's why it shifts K, right? That's why K changes, because we're actually changing the concentrations of our reactants and our products. Okay, so any questions about exothermic, endothermic? We're going to go into crazy detail of this when we get to thermochemistry, but I just wanted to make sure we kind of remembered what it was. Just remember endo, like entering side. It goes on the reactant side. Exo sounds like exiting. It goes on the exiting side of the equation, the product side. So that's really what you need to remember about endothermic, exothermic right now, right? If you can just remember those two things, you should be good for this chapter.